Okay.
Sì, benvenuti a tutti all'8º seminario webinar della SIE. Questo paper interessante che confronta il caso, le politiche di lockdown verso le politiche di non lockdown, a quanto capisco in particolare il caso svedese. Forse la presentazione sarà in inglese, ma per tutto questo do la parola a Donato che coordina il seminario. Donato, a te la parola io giusto per salutare tutti quanti.
Yes, thanks Alberto. I am Donato Romano, the Vice President of the Italian Economic Association, and it is my great pleasure to introduce very briefly this 8th webinar of the Italian Economic Association on COVID-19 and the economy. As probably some of you know, some of these seminars, we started with some seminars that are mostly focused on the macroeconomic side. We had the first seminar in particular by Guido Lorenzoni and colleagues on the macroeconomic implication, and the two other seminars, namely the one by Donato Masciandaro and the other by Botta et al., that were mostly on the monetary side. So some policy interventions, helicopter money from one side, and demonetization and EU recovery bonds, and an analysis and assessment of how they work in order to try to buffer the impact of the COVID-19 outbreak. Then we had also a second cluster of seminars that were mostly on, say, the supply side, talking about the value chain disruptions and their implication. This is the seminar that have been organized by Roberto Rabellotti, Anna Giunta, Michele Ruta, and Luca Salvatici, as well as Massimo Florio, who talked about the EU biomed infrastructure, a new EU biomed infrastructure in order to overcome the pharmaceutical oligopoly. Over the last two seminars, we moved a little bit the focus towards more micro topics. And we had a first seminar by Guglielmo Brescese and colleagues that were on the behavioral, some behavioral consequences of social distancing measures in Italy. And last Thursday, we had Leonardo Becchetti and colleagues who analyzed in a quasi-experimental context the role of lockdown decisions and of poor air quality in Italy. This afternoon paper is looking actually at the flip side of Becchetti and others colleagues. It is an evaluation, again, using quasi-experimental methods on the non-intervention, non-lockdown. And this has been will be presented by Eleni Ilioliou, who is lecturer at Queen Mary University of London in the School of Business and Management, and I thank her for her participation, and Giovanni Cerulli, who is the first researcher at the Research Institute on Sustainable Economic Growth of the Italian National Research Council. So the rule of the games are the usual ones. The speaker has 40-45 minutes in order to present his own paper, and all the ones who attendees who would like to intervene, please use the Q&A facility, and we try to summarize your questions for the speakers. So Giovanni, thank you for participating. You have the floor. Please.
Thank you very much, Donato, and I would like to thank you, Marco and Alberto, for your invitation. It's a real big pleasure for me to present this paper, and this is joined with Eleni, and so the paper is about an evaluation of the non-intervention policy in Sweden, and basically we would like to understand the effect of the lockdown implemented in Europe, using as a case study, as a special case study, the Swedish case. Okay, that's more or less the in few words what we have done. So let me start with a very initial presentation of the topic. Everybody knows what COVID-19 is. Is an ongoing epidemic, unfortunately, that hit very severely people all around the world now, starting from China and then moving to Europe, to then spread over many other countries in the world. So at the moment, I think that the best thing is to start directly with the background. In the background, I will try to give you some idea about some anatomy of the epidemic or the epidemic phenomena, because I think that even if this is not strictly speaking the very center of this presentation, I think this might be very useful for us to know what is this anatomy. Okay, let me start from a very nice, not nice in the topic, but I would say in graphically speaking, I would say antecedent for the COVID-19, which is the Spanish flu. As you can see, basically, this pandemic lasted 2 years. 2 years means that it started from the end of June in 1918 and ended up around May of 1919. And as you can see, during the Spanish flu, mankind experienced 3 times of very active wave of this pandemic, and especially we see that we have basically a new big emerging pandemic some months after the big one experienced during October and November 1918. So this is a bit worrying for us because we are now coming out, so we are pretty here now, so we hope not to get another one big wave in the next future, and this is what we would like not to happen at all, of course. So this is important because we are looking at the death per 1,000 persons, and this is basically the main target of this presentation, because we are going to speak about death per million of people. Okay, so the main target, the main outcome is exactly this one. So for this reason, may be interesting to look at this. Okay, let me start now from some arithmetic of the epidemic. I know that everybody is quite knowledgeable about this scheme, because in the news, in the broadcast, we are pretty all the day hit by this kind of graphs, and everybody knows about it. However, it may be interesting for us to better just repeat what is the arithmetic of the epidemic. Then the total cases, remember that the total cases are the sum of 3 components. The total positive in time t, the total death in time t, and recovered people in time t. So it is extremely important to understand this, because according to what we are going to see, we may have a different picture of the epidemic phenomenon. And in particular, it is extremely important to say that the variation, what we see as the new cases every day, is the variation, is the delta of the total cases, right? And so we have an adjustment, like a sort of complement between the total positive and the death and recovered. Why? Because as long as time goes by, we have the people get recovered or unfortunately can be die. So basically, this identity is all the time true. I just represented for convenience the graph, the time pattern of these quantities, and for Italy. and nothing special. It's just for you to catch the main meaning of this identity. Okay, let me, however, try to understand, to speak a bit more about the anatomy on an epidemic. Because this is a big topic. It is not possible to summarize it in a presentation of 35 minutes. However, I would like to say that the very center of this anatomy is the speed of diffusion. The speed of diffusion of the virus is the very center of any analytical understanding or analytical model of the epidemic dynamics. And the very key parameters is the replication number R0. Maybe many of us all the time have heard about it. But anyway, the main point is that the replication number is the average number of infected people per one infected individual. So as long as we have that this value is larger than 1, we are in what we economists generally we call increasing returns. And this increasing return is typically found during the first phase of the epidemic. And so the virus is able to spread very, very quickly and in an exponential mode so that the virus can thrive, right? And there is the opposite situation, which is a situation of decreasing returns, of a weakening process of the virus diffusion, which is when R0 is smaller than 1. This is typically found during the second phase of an epidemic. And in this case, there are many people that get recovered or unfortunately that die. But the healing speed is now higher than the contagion pace. And so the virus starts to die, and finally we are recovering day by day. And this is what we had experiences at a certain point when we pass, I would say, the peak. And I'm going to show in the next slide. This slide is very important because it expresses the dynamic of an epidemic. This is very general. This is not strictly linked to the coronavirus. This is very general for any epidemic. Fortunately for us, the epidemic has a bell-shaped form. So although it may be very severe, at a certain point, it fades away. And so finally, we have that it ends up to be 0 at a certain point, 0 number of positive cases. But this structure, which is generally approximated by a generalized gamma distribution, or if you want, is a normal one in this case, but is a much better caught by a gamma distribution with proper parameters. As we can see here, we can define different moments in this distribution, different phases. And in particular, the one in which we have increasing returns is the explosion phase, and is at the very beginning of the epidemic. At a certain point, as long as we go through this through time, and this is the number of days, we see that we reach the flex. The flex is when the R0 turns to be lower than 1 from being larger than 1. And so we get into the implosion phase, which is the phase of decreasing returns. And then we go back and we go ahead, sorry, until we have saturated all the positive cases. In each point, because we are measuring here the total positive cases, in each point, for example, in this point, this is the number of positives, and this is the number of death and recovered people. Okay, so basically this is what we have. This identity is always hold during along this dynamic of the pandemic. And finally, of course, we have the pandemic saturation. This is the typical sigmoid form of the pandemic, generally, because this is the total cases, generally people report this one as the main epi curve. But anyway, I want just to show you that the very dynamics is caused by the dollar positive cases. And in particular, we have the famous peak. I also did a paper. This is published now, but not published. This is just in the AF COVID page, in which I try to forecast the peak some months ago. And in the mid of March, in the last week of April, more or less 10 April, we managed in Italy to reach the peak. So to downturn, to start the decreasing pattern of this, the overturn, sorry, the peak, and start the decreasing patterns of the epi curve. Okay, that's pretty old. So the derivative is the pace at which it happens. Okay, so the derivative of this curve is extremely important because it is the measure of the pace. Okay, this is just for us to understand a bit of this. This is exactly, would like to say, an observational counterpart of this one. So this is a theory and this is practice. And this is exactly this curve, the two curves measured for China. And in particular, China was at the very beginning of was basically the country where the COVID started. And so, as you can see, these are the total cases having the typical sigmoid form, even if it is not wonderful as in the previous case. I assure you that it's a sigmoid, and these are the total positive cases. So you see that the dynamic is really in the phenomenon as it is, and it's very general. Okay, the very point is, suppose that we have a situation like this, and we know that the structure, the inherent structure of the epidemic phenomenon obeys this kind of curves, this kind of dynamic. So might it be interesting to ask us, what are in which way we can tackle this the spread of the virus? And we have two options, two roads to hit, basically. Pharmaceutical interventions and non-pharmaceutical interventions. Pharmaceutical interventions are, of course, the most relevant, I would say, as long as we have solutions, of course. Targeted drugs in order to cope with the symptoms of the COVID-19, swabs and blood tests in order to identify infected people, and vaccines, of course. As you know, we have done quite well now in this part, because now doctors are much able than they were some weeks ago to tackle the COVID symptoms. And also we witnessed a big increase in the swabs and blood tests in order to detect infection. We are a bit, we are lagging behind with the vaccine now, but just because, as everybody knows, it takes time in order to be carried out. Non-pharmaceutical interventions, on the contrary, may be another possible option in order to cope with the spread of the virus and in order to weaken the spread. And we know there are many different possibilities, and this possibility have, of course, large social costs. In particular, social distancing, border closures, school closures, isolation of symptomatic individuals, traveling restrictions, protecting devices, for example, all the masks that we are now obliged to use anytime we have to go out or to have contacts with other people, and large-scale economic lockdown, which has been a very drastic, very strict intervention, but at a certain point needed in order to reduce the strength in the spread of the virus. So this work is mainly focused on this. Of course, all these also is contained sometimes somehow in this. Okay, that's the point. Okay, what are the expected effects on non-pharmaceutical interventions? This is an interesting question because, of course, we have to apply this scientific reasoning in order to reply to this question. It's not just the idea that, oh, if we are distant, we are safe. It's not just about this. We have to understand the dynamic and the structure of the phenomenon in order to respond to this question. So interventionism is a way to avoid herd immunity, okay? And it entails three fundamental modification in the shape, in the structure of the epidemic phenomenon. The reduction in the number of infected people by lowering the peak, the delaying in the time at which the peak occurs, and the extension of the saturation time, the end of the epidemic. These are the three main possible effects an intervention can have, and we can see this in this graph. This graph clearly identifies what an intervention can do. Okay, this is the phenomenon, the epicurve, without intervention. What we see here is that it is very tall, so having a very large peak. It is quite strict around the I would say, the central date, the day of the peak, and is also short because it lasts in less than 100 days, right? So this is just a simulation. It's nothing really special. So do not take this. This is just a theoretical distribution. What happens when there is intervention? What we expect intervention to produce? Well, the first thing is the time extension, as I said before. So it means that it lasts more. So the intervention generates slowdown in the epidemic phenomenon so that it lasts more. So we have to accept that it lasts more. The second, the more important thing is that we have a very big reduction in the height of the peak. The height of the peak becomes shorter, and it reaches the healthcare system capacity. For example, this should be, in theory, able to comply with the number of beds in intensive care, for example, or in other medical indicators. Okay, and finally, what we see is that there is this is an intensity. This is the movement on the right. So it means that not only it lasts more because it's a spreader, but also is being shifted rightward. So it means that we reach the peak later because of the intervention. Of course, all this was made in the hope to avoid many deaths, in avoiding a larger and more severe form of this epidemic. So, in other words, to avoid to stay here at this point, which is very dangerous. So the choice was to have a phenomenon that is shorter but more intense against a phenomenon which slows down, which is more extended over the time, but that is also less severe in terms of the people hit by this. Okay, so now we want to focus on a peculiar kind of intervention, which is the lockdown, right? And we experience, and we still are experiencing partly the lockdown in different phases. So the lockdown was a necessary step, a necessary policy, because the European Center of Disease Prevention and Control was found to be really unprepared to deal with the severe situation generated by the coronavirus. It was really unexpected on the one hand, and probably we were unable to cope with this big problem. And Europe at the same time became at a certain point, the epicenter of the pandemic. Now it's South America, but anyway, Europe at a certain point, and especially Italy at the very beginning, was very heavily hit. And and many countries decided to get into locking down the economy. And it was a really serious and very hard choice for many reasons. And as you can understand, as everybody knows, and in order to avoid what? Exactly to avoid this situation and possibly faster but much more severe form of the epidemic. Dynamics of the epidemic. The only country that did not get into a rigorous lockdown was Sweden. So Sweden is an interesting case. Why? Because as I'm going to explain later on, basically, if we want to analyze the effect of a policy intervention, we need a counterfactual. And if every country in Europe experienced the same lockdown, so even if in different dates, it is clear that we do not have an available counterfactual. But for Sweden, it's different, because Sweden can have a counterfactual, although not a perfect one, as we are going to show. But anyway, it is potentially possible to define a counterfactual for Sweden. Okay, because getting into this, it is important also to see that the level of intervention and the timing has been, I would say, has had different phases, from less severe to more severe and more serious policies. At the beginning, we have just self-isolation that was in some sense recommended but not obliged. And then social distancing that was encouraged, then public event banned, so closure of the school ordered, and finally the lockdown with many companies, factories, shops closed, completely closed. So a very lock of the economy for 1 month and more. So this is what happened, and in different countries, as you see, depending on the fact that the COVID appeared with some delays in different countries, first in Italy, then moved to Spain, and then the UK, and blah, blah, blah. So we see immediately that we have this distribution of the different policies over time. Okay, this paper has as a main objective the one of evaluating the Sweden no-lockdown policy, in particular on the effect on the number of deaths that Sweden experienced. We use as a counterfactual approach the synthetic control method, and the question, the central question we would like to respond to is, what would have been the number of deaths in Sweden had this country implemented a lockdown? This is the main question we would like to reply. Okay, there is nothing better than start with a non-causal analysis. So if you want, this is just a descriptive analysis. Okay, the descriptive analysis, however, is extremely important because it is exactly what happened. So when we speak about the before-after estimator, is exactly what happened in the reality, what we observed. So we start from observation, and then as scientists, we try to respond and we try to dig into the data in order to provide causal statements. Okay, the first slide just to represent the death per million in Europe, and as you can see, we have that Sweden, although it was a small country and also although experienced the COVID occurrence later compared to other countries, has a quite big, quite a sizable increase in the death per million inhabitants. Italy and Belgium, of course, at the time where we caught this, sorry, had a very severe situation, as we know very well. So this is just to, I would say, give an image of what was going on. This is the pre-post lockdown pattern. And the vertical line, let's say, for example, for Austria or Belgium, is the date at which they started the lockdown. And as you can see here, the after pattern may be a bit different in different countries, although we observe, of course, a greater rise in the number of deaths per million, but just because this is the epidemic structure made this way, not because of the lockdown, of course. But we do not know what would have been the behavior or the pattern, let's say, for France, if France had not been doing the lockdown. So this is just what we observed before and after. And we see that in some cases, like France or like Italy, because they were a bit more advanced in terms of the pandemic phase, we see that we already observed some the curvature is that one of a decreasing return with an R which is smaller than 1, if you want. In other countries like Finland, because the lockdown was implemented at the very beginning, in some sense, of just as a preventive intervention, we see that the pandemic was still in the very explosive part. Remember, and the flex is more or less here, the flex, right? So in this point. And Germany is pretty the same, and blah, blah, blah. So we have many different situations. So just to measure the before and after, we get exactly a measure of the before and after situation. And again, we see some not very new news, I would say, new figures, because everybody knows that Belgium was heavily hit, like Italy, France, Spain, and the UK, and other countries a bit less. Observe that we are speaking of total death per million inhabitants. So this measure is already standardized for the size of the population. Okay, so they can be comparable in this sense. And there is a very different dynamic, different size for different countries. Of course, most of them, it depends on the phase at which we are measuring the phenomenon. So I want to say that this is high just because Italy was experiencing the coronavirus from several weeks compared to, let's say, Ireland or Hungary. Okay, that's the point. So if we look at this data, we observe a problem, or two problems, I would say. The first problem of just looking at what happened, just by looking at the before-after estimation, before lockdown, after lockdown estimator, is that it collapses two effects. One is the effect of countries' different phase in the coronavirus development. Some were at the beginning and some were not the end, but in a more advanced status. And one is due to the lockdown, of course. So we cannot disentangle the two by looking at this. And there is another third problem, which I consider the most relevant in this case, which is the lack of a counterfactual. So it means that we cannot compare Italy with another country because all the other countries experienced the lockdown. So, or at a certain point they did, or we don't have enough time in order to spread our comparison in a longer time spell. So we cannot draw from a before-after estimator any causal statement. We cannot say that, for example, in Italy, the lockdown was better, was more effective than in Spain, or was more effective than in France, or whatever. This is not possible to be done here according to this problem. So we need causal analysis of the lockdown effect. And for this reason, we use the synthetic control. And I immediately want to say that we are going to cope with all these 3 points, I would say, especially in the first case, the first point, sorry, can be, for example, faced by introducing the lags of the potential of the outcome variable of the target, because the lags are able to catch the initial state of the pandemic. So in some sense, it is able to clean out for the possible presence of different stages, different phases in the pandemic evolution. And of course, in this sense, we can catch much better the lockdown effect. And of course, we may, just for Sweden, to be honest, we may have a counterfactual in order to provide causal statements about the effect of the lockdown. Okay, in this sense, Sweden is an interesting case study, and the only one that can be exploited in order to provide a causal analysis instead of just a monitoring or a monitoring analysis. And because we need a counterfactual, and Sweden has many counterfactual, as many as the number of European countries that decided to get into a lockdown. So it is an interesting experimental case study that we can pick up in order to understand whether or not the lockdown had an effect. So we are a bit demanding in what we want to do, because in some sense we would like to use Sweden in order to know whether the lockdown was or was not effective. So it's a very big endeavor, I would say, a big challenge. And this one relies on whether or not Sweden can be a sensible case with large external validity. Is Sweden, as the Sweden case, some important external validity? If yes, we can say that what we have found is something that can be generalized to other countries, and so that it may be extended to other countries. On the other hand, if we say no, the external validity is very small, it's very poor, so probably this is just because the results we get are just results that are able to enlighten us about the Sweden case. It's just about Sweden and cannot be generalized to other countries. Anyway, let me get to the point later on. For the moment, we want to stick around the SEM as a case studies for policy evaluation, and we think that because we are working with just one single treated, Sweden, to be clear, in this case, treatment is the absence of the lockdown. Okay, so just to be clear. And because we want to work with, we are obliged to work with just one single treated, so it is proper to use the SEM. So I want to speak about the SEM as a general methodology when that can be used exactly for case study inference and case study program evaluation, where case study means that we are relying just on one single treated, right? Treated unit. Okay, the SEM belongs to the difference in differences family when we have just one treated, okay? And the basic idea is to producing a counterfactual via a combination of several untreated units. Remember, these untreated units are sometimes called donors in this literature. And the main validation test for the SEM to provide reliable results is the parallel trend achievement. So we would like to find that the actual and the synthetic before intervention had the same pattern. Basically, they were not distinguishable. And the very core of this analysis is to generate an optimal weighted scheme that we can use in order to combine the different treated of the different donors. Another important characteristics is that the SEM is also interesting because it does not provide a standard inference. The inference provided by, so in other words, the significance of the result provided by the SEM is very poor, but at the same time very intriguing, I would say, because it requires not conventional t-tests, in other words. And finally, in the last year, it has been it has been characterized by several extensions. One is also mine, and I provide a non-parametric development of this methodology in my paper in Economics Lectures, and I'm going just to give these. And we use, in this case now, I'm going to speak about now this methodology, just a few minutes. And I would like to say that in this methodology, we have one treated unit and J available control units or donors. So the very center of this analysis is to find a vector of weights that are positive, or I would say not negative, and that sum up to 1. And we would like to find these optimal weights, because of course we may have many of these, in order to get a trajectory of the synthetic treated before and the actual one before intervention, which is the same or very, very close one each other. Not the same because it is possible, but very close. So the main idea is to collect a series of the pre-intervention outcome predictors, X1. So X1 are, suppose that we have K predictors of the death generated by the COVID, and we collect them into this vector. And then this is for Sweden. 1 is Sweden because it's treated. And we exactly do the same for all the other donors of countries in Europe. And we have a matrix X big 0, which is exactly a matrix with K rows and J columns, okay? And then by giving a different weight to different predictors, for example, I might want some predictor to be more relevant than another, we can generate a loss function. And this loss function is nothing but an OLS, if you want, in this case, because it's just the main idea is that we want to minimize the distance. Is the distance between the pattern of this vector and its projection, this is the projection over the vector span, the vector space spanned by these subvectors, these matrices. In other words, we want to find omega in order to have to see that the actual and the synthetic, which is nothing but than this, have to be as smaller as possible. Okay, so we want to minimize this distance and find the optimal omega as the one providing the minimization. Suppose that we were able to minimize this, and suppose that we know this omega and is omega star, then if we collect the vector or the outcome, or the time series basically of the deaths in for the coronavirus in Sweden, and all the other ones, all the other time series of the deaths in the other countries, then what we can obtain is the counterfactual outcome, which is now Y1 star 1, which is nothing but the product of these two vectors. So this matrix times this vector. Is this a linear combination of the single time series of this of each single country multiplied by its own weight? And the weight reflects the closeness of Sweden to the other countries. So we are expecting that Sweden will be closer to northern countries than, let's say, Greece or Italy. So probably we find a larger weight for, let's say, Norway or Denmark or Germany and blah, blah, blah. Okay, this is not our result. This is the result by Abadie and Gaddeal that are pioneering this approach. And as you can see, finally, This is the case for Basque Country with and without terrorism. But what is the idea, just to deliver the idea that we can finally trace the pattern of the, of the synthetic and the actual. How can we measure the goodness of fit? The goodness of fit is exactly this part. You can see the goodness of fit in this part. This is the parallel trend. Or in this case, we have not only parallel trend, we have a perfect identical trend, which means that also we managed to get a good balancing in the data. Anyway, the main point is that we want to take the average of the distance year by year, in this case, time by time, of the synthetic and of the actual before treatment. And so we can measure this in a single number, by a single number, the root mean square error, the root mean square pre-treatment error, sorry. Then we are going to find to minimize this difference. Sorry, here there is a square here that is not reported, that I forget it, but is of course is a Euclidean distance in this case. What about inference? Can we do inference with one treated? No, we cannot, of course, because when we have one single treated, we don't have enough, I would say, wheat to cook the cake, right? So it is impossible to get the standard errors. Of course, it's like to have a test in which you have just a sample of size 1. So with a sample of size 1, you cannot have a statistical test. How can we provide a test in this case? How can we say that, let's say, this difference that we observe here is in fact significant? Just by using a permutation test. A permutation test is similar to, even if not, is a computational approach, similar to, I would say, the bootstrap, but it's not based, however, on random draws, but it is used on the placebo reasoning. What is this? Basically, the main idea is to generate the distribution of the t-test by rerunning the same model over the untreated donuts, untreated countries in this case. So the main idea is that if and only if which is the reasoning behind, is that if for Sweden, in this case not Sweden, in this case it's California and among several US states, but if the treated has a very, very unusual pattern compared to the rest of the other units, when they use it as if they were treated, but they weren't, but anyway, as if they were treated. So if this pattern is very peculiar and lays in the tail, then we can conclude exactly that there is a significant effect. And it's exactly like to say in a standard T distribution that we are in the rejection area. So for this reason, we can accept that we can reject that the effect is 0. And this is what we would like. Our setting. In our setting, the unit of observation is, of course, is the country level panel data, before and after lockdown observation. This time spell goes from 15 February to 2nd of May. And this is a very important point, how we rescaled the treatment date. In fact, the lockdown started in different times of the country, right? But the SEM works exactly when we have a fixed time treatment. So the treatment has to be fixed over time. So we rescale the starting date of the lockdown as if all countries experience it in the same time. Then, after this rescaling, we consider 24 days before and 40 days after lockdown. And what about Sweden? Sweden has not a lockdown, so how can we center Sweden in a proper way? Well, we consider at the center, in the Sweden case, not the lockdown because they didn't experience it, but the day of the first death. The day of the first death for coronavirus is exactly the day we are going to consider for Sweden. And then we again consider 24 days before and 44 and 40 days after this date. Okay, choice of the control variables. Remember that the control variables are important for us to get a good pre-treatment common trend. So in order to provide balancing and in order to provide a pretty perfect precondition for or validation condition for our SEM, we need to use a very good control variables. Of course, the control variables should be those that are basically pandemic diffusion drivers. And we consider first factor reflecting the percentage change in the movement of people. This percentage change is made according to, or as having as a reference a benchmark, which is before the epidemic condition. So situation. And we are going to measure the movement in people for retail and recreation, grocery and pharmacy needs, pharmaceutical needs, parks, transit stations, workplace and residential areas. All movements that are in some sense linked to this peculiar topics. And characteristics of the population, median age and the number of people above 70 years, and the index of hospital capacity, the number of hospital beds per 100,000 people, okay? So this is the main point. I get immediately to the results. So we run basically synth, which is this has been carried out in Stata by Abadias, Mueller, and Diamond. And then I try also, just for fun, the NP synth, the one I did for Stata, which is the non-parametric approach. I didn't have and I don't have the time to speak about this methodology. So for the moment, take it for granted. Okay, this is the main results we have by synth. Okay, first of all, as you can see, we have a series of countries that have been selected. As you can see, the selection has been is quite reasonable because the most important countries that are comparable, that are donors, are Norway and Denmark and Norway, and then Finland and Estonia. So they are Baltic and Northern and Scandinavian, other Scandinavian countries. So Sweden, of course, this is very reasonable for Sweden, right? So it makes sense. On the other hand, we have the pre-treatment balancing in the predictor is very good according to the weights we have found. As you can see, for any of these variable, we get reliable pre-treatment balancing. And the root mean square error prediction error is very small and nice. So if I look at these, I would be very satisfied about what we have found, but it is important to see what we found in the analysis. So before getting into the result based on these weights, it is interesting also to compare Sweden with a very sharp unweighted average of the European countries. And as you can see, if we were looking at just this one, we would be very tempted to say that there is not a strong effect. And on the contrary, that the effect is a bit mixed up. So this is why, because in this case, Greece, Portugal has the same weight as, let's say, Denmark and Norway for Sweden. So it is really unreliable to look at this result. So a sharp average, or if you want, uniform weights over the donors might be very misleading. So again, this has not a causal interpretation. This is the main result of this study. And this is the causal effect we try to catch in this case. And as you can see, this is the timing of the lockdown, remember, and this is exactly the two different dynamics of the actual Sweden, what Sweden actually experienced in terms of death per million inhabitants, and the synthetic control. what would have been experiencing had Sweden accepted to get into the lockdown. And you see that there is a coefficient of 3, is a 3 times larger the effect, the cost in terms of death, the costs in terms of death for Sweden has been 3 times larger than with a possible lockdown. So it's a quite sizable effect, and in some sense really, really strong. Now the very problem is, okay, Gio, Eleni, you are saying that this is very strong effect, but can you come up with a test of significance for this? Can you say that this is strictly speaking overall different from 0, especially at the very end? And again, we have to use a non-standard inferential approach, in this case, the placebo test. So what we do is to run the placebo test in our case. And we are really happy about it because, again, you see that this is the theoretical t-distribution and we are in a tail. So Sweden is in a tail, so is in the tail, and it means that we are quite strongly positioning Sweden in the rejection area. So we reject that this difference is equal to 0. This difference, which is a difference of 100 deaths per million, 100 deaths per million, is significantly different from 0. Okay, finally, I tried just for fun the synthetic control method using the non-parametric approach, and the result is not really nice, to be honest, because we have, yes, that from a certain point on, the synthetic is below the actual, but with a difference which is much smaller than the one we have seen before. And more importantly, the method this time didn't manage to get an RMC very small. And also we have a larger number of country donors involved, and with Denmark, Finland, Norway getting higher weights as in the previous one, and this is correct, but not getting a great job in terms of balancing. Why? Okay, I have to explore it a bit better. My impression is that when you have a few numbers, and we are not working with a lot of data, a non-parametric model are really biased in general, and we know this very well. And they work very well, and they get very reliable results, better than parametric one when we have a larger mass of data, especially when n is big, the size of the sample is big. And the other point that probably counts here is that this pretreatment period is full of zeros. So it is sufficient to have a non-zero point for some countries that the non-parametric fit gets a bit crazy, but very, very unstable. So this is my intuition of why the method that has been proved to increase in the precision compared to the synth, and this is for this reason that I published the paper. This is my intuition of why it didn't work well in this case, because the data are really, really peculiar, really, really strange. So I get to the conclusion. We think that we have found a sizable causal effect of the no-lockdown in Sweden, and that this quantity is quite sizable. Is 3 times the number of deaths that Sweden would have been experiencing and not locking down. And in terms of robustness, even if they are a bit different in terms of qualitative results, we see anyway that even in the non-parametric case, you have that the effect of the synthetic is smaller than the effect on the actual, of course. And then we have 2 other questions that I would like also to leave to the floor to discuss. The external validity. Can we extend the results to other European countries? Can, in other words, say that in general, also for Italy, also for France, also for Germany, there has been a 3 times fewer number of deaths thanks to adopting the lockdown? my impression is that my hope would be yes. But the external validity, especially because we are considering a very peculiar country, which is small, Nordic, isolated by the rest of Europe, like isolated geographically, I mean, like Sweden, probably maybe not a perfect example. And very finally, cost-benefit analysis. And many people also try to balance the cost side that with the benefit side, reduced job losses, milder income downturns, and probably less smaller social costs in general. I leave to the floor the question because the benefit side, so the lockdown may have also may have had, it may have also in the future severe impact, for example, on suicides, or if, for example, some companies get in bankruptcy, probably the owner can get suicided, and we don't know. So the cost sides also of the lockdown are maybe sizable, but we don't know about it. So I think that other studies should look also at the benefit side. Thank you very much, and sorry if I didn't respond to the questions, but I think there is time now for Donato to pose me all the questions you need. Thank you.
Yes, thank you very much, Giovanni and Eleni. So we have just a few questions to begin with. I would like to start with Alessandra Morese's question that was referring to one of the first slides that you showed. So why did you choose the Spanish flu as an example for evolution of the pandemics? To the best of her knowledge, the Spanish flu was mainly affecting children, so it might be different from COVID-19. Basically, is the Spanish flu compatible with the COVID in terms of other parameters? That's the question.
Okay, sorry, no, I don't have a very sound response on this, because this is just for putting into the emphasis the fact that the pandemic can have a second wave or even a third wave. So we experienced this, but we experienced this also in other cases. If we look at some history of pandemics, also another one which was maybe in Portugal, and they see that we have different waves. Probably not of the same severity, but we may have a different waves. Of course, the two phenomena are completely different and cannot be comparable in some sense, because they appeared in different times and with a different spread, and also with a completely different dynamic and ability also to cope with. So I'm not able, because I'm not a virologist, I'm not able to respond very well to this point. I'm sorry. But anyway, this was just to say that the pandemic may come back, unfortunately.
Okay. So the second question is from by Tommaso Aquilante, who is asking you, as others, if have you seen the paper by Bourne et al. 2020, which do the same thing on a very similar time span, but finds very different results?
Probably yes. If he refers to one paper that has been published recently as a working paper, we have seen that. We are still trying to understand a bit better what are the main differences between our paper and the paper of these guys. And at the first sight, we realized that they used a smaller number of countries. They did not do a placebo test, and possibly, yes.
Variable is also
yes, sorry, Eleni, it is very important. And they did not use all the controls we use, controls for the possible, all the possible movement of people and characteristics. Eleni, do you want to add up something?
No, it was not so much on the, we added some more controls, but we were looking at the death per millions of people, but they were investigating the spread of the disease, so not the death rates per millions of people.
So there are many differences.
Yes.
Yes, there are many differences, but anyway, we are aware that we have to in some sense confront with the other papers with a similar topic, of course. Sure.
Yeah.
Thank you.
Since we are talking about control, let me just make a comment here. I think that the sets of control that you used are quite good, actually. I mean, if not else, because your results seems to find out a significant effect there. But there are at least a couple of controls that could be quite easily introduced and could be relevant. The first one is religion. A religion in the sense of behavioral attitude of the different populations, you know, say Protestants versus Catholics, okay? Because one of the claim that the government of Sweden made was that they were much more disciplined in order to try to respect, you know, physical distances instead of locking down the economy. And the second one, even though this is quite disputed right now, it seems that some epidemiologists place a lot of faith about the different behavior of this virus in terms of temperature, and there is a gradient between Sweden and the southern European countries. Okay. So probably this could be also something that could be included in your set of control. Anyway, we have Luca Favero, who is emphasizing that using the synthetic control method, he was asking, have you tried to assess the robustness of your results to different treatment dates for Sweden?
Okay. That's a good point. Yes and no, in the sense that we try to do, we would like to do it, and it is part of the robustness check that we are going to do. It is correct.
We did a little bit of this, Giovanni, and we were getting.
Okay, Eleni, explain. Yes.
Results. We were if I understand the question all right. We did move the lockdown date of Sweden a little bit before what we had originally introduced as the lockdown date for Sweden, which was the date that the first death in the country occurred. So we did a little bit of that, and we didn't find anything significantly different. So the picture is what Giovanni presented.
Okay.
Yeah, that was the picture that we were getting. Yes.
Okay, and now we have a question by a Swedish, I guess, attendee. The first comment is the mortality in the short term should be balanced against immunity and strength of the second wave. Sweden has rather high immunity. How is this considered in your conclusions?
Okay, the mortality in short term should be, okay, I was reading, sorry, I was reading the second point.
Yeah.
The mortality in short term should be.
Actually, I think that by not locking down, Sweden will develop a higher immunity. And so in the case of the second wave, this will be an advantage. Basically, this is.
Yes. This is a good point. In my opinion, the point that Matthias raised is the benefit side that we're not able to measure. So this is not an anti-Sweden approach. Okay, it is for this reason that I was we were really careful in also speaking about the benefit side that we were unable to catch in this case. But this might be possible to have an higher immunity, maybe in the event of a second wave. This might be an advantage that for Sweden, of course. Yes, I'm right. Sorry, I agree with you. You're right.
Yeah. So a second comment by Matthias is related to the heterogeneity within the unit of observation, the country, Sweden. So he was saying that there are significant differences in mortality. In the region of Skåne, 1.4 million, the mortality is 6.7 times lower than in Stockholm. So is it reasonable to conclude that the effects are related to lockdown, which has been applied in the same way in both regions?
Okay, this is another very interesting point. And I think that this is the same problem we experience in Italy. When we speak about Italy and COVID, of course, this is a strong, super strong regional dimension. And as we know, as everybody knows, probably if we exclude Lombardy, Piedmont, Veneto, and Emilia-Romagna, probably, and especially Lombardy, probably all the rest of the countries was just very slightly hit by the COVID. So yes, you're right. Unfortunately, I would say that probably what one can do is, but I have to think how to do it, is of course to run the same kind of analysis at a regional level. So possibly a European regional level, I mean. And this might be something that can be exploited in the future. For example, using also a time varying and also a space varying treatment, which is strictly speaking an extension of the very, yes, I agree with you, simple and rough approach that we, geographical approach we have run using countries. But you're right, I agree with you.
Yeah. Giovanni, I have also a question myself, you know, taking advantage that you are an expert on impact evaluation. It seems to me that, you know, when you talk about the synthetic control method, actually, there is no economic framework or a theory behind it, actually. It is basically a statistical method to build a counterfactual that is a sort of artifact, right? And this severely limits the policy implications that you can get out of it, except for the treatment that is the only, say, shock. In this case, it is the treatment variable, the policy that you are analyzing. I was just wondering if there is anything that you can get out of the predictors that you use in terms of enrich a little bit the conclusions that you are getting from your study, or am I completely out of the blue when I try to do something like that?
Yes, this is a very interesting point. It's a bit more general than just the synthetic control method.
Yeah.
It is a problem of all non-experimental approach, and even more for the experimental one, in which even the covariates are useless in some sense. Mm-hmm. And yes, the very point is that they may be black boxes. So in other words, you get the result, but you cannot how to disentangle in some sense, or to give more emphasis on the potential, for example, use of other variable in order to analyze the potential different effects of a combination of outcomes and of covariates and blah, blah, blah. So the problem is very general. So my point is that this is a very reduced form model, in the sense that as long as we are going to use reduced models in econometrics, the more we use reduced form, the less we can say about I would say, the managing of the policy. For example, move these and what is going on if I move these, if I change these, blah, blah, blah. But the more I can be precise in catching the effect, like in a prediction inference trade-off in some sense. And there are some methods that are able to mix up a bit the things. So that are a bit less reduced form, a bit more structural, and that are also able to see what is going on, for example, in single groups, single elements, for example, covariates, if you are going to, let's say, fix one covariate at a certain point and blah, blah, blah. For example, there are some methods like more regression-based methods, basically.
Yeah.
So what I say is that yes, I agree with you. I don't have here the theory enters in the choice of the covariates and in the choice of the sometimes in the treatment, if the treatment maybe, let's say, it's very rare, but maybe questionable when treatment is or what treatment is. But it's basically this one. Then after this, I think that what one can do is to start from this analysis and then to build some more structural models in order to analyze a bit more the many effects. For example, all the analysis of the mediation analysis is completely out of this. The mediation analysis,
yes,
in this case, you do not know, for example, the lockdown may have a different impact on, let's say, economic and health or in another variable that at the same time can have an impact on another variable. All this is behind the picture, is not in the picture. Yeah. It's completely behind. This is a big problem we have when we work with very reduced form models. Now they are fashionable, they are very used, but we have to remember that economy sometimes wants to open up the box.
Indeed, yeah. Okay, so I would like to thank you all, both, the speakers, so the authors and the speaker and the attendees. It is 6:20, so it is time to close this webinar. I think it has been very interesting, and if I may, Giovanni and Delaney, I would invite the attendees that have some specific questions or comment. They can approach you, emailing to you. Your email. Would like to tell the attendants what are your email, Giovanni?
Sure. I can, if you want, I can put it into the slides, and when you're going to put the slides into the website, you can find it there.
Okay, so thank you very much, and I would like to give the floor for just a final comment to Marco Cocculelli, who probably has to say something for the next webinars. Please, Marco.
Thank you very much, everybody.
Grazie ancora Giovanni, torno all'italiano, grazie a Giovanni e grazie a Elena. Sì, io farei chiudere ad Alberto, in realtà prima di passare la parola ad Alberto ricordo il prossimo seminario giovedì 2 luglio, Chiara Punzo e Lorenza Rossi sugli stimoli fiscali finanziati con moneta. Alberto, ecco, sì, lo vedo in linea.
Grazie Marco. Però giusto per ringraziare Giovanni e Eleni per il bel seminario e a tutti coloro che hanno seguito il seminario. Mi sembra un seminario molto interessante, abbiamo imparato tante nuove cose. Grazie mille.
Grazie a voi per l'invito e per la possibilità di poter presentare questo lavoro che ovviamente ancora deve essere finalizzato, ma che comunque è in un buono stato di avanzamento. Grazie per i commenti e per l'opportunità.
Grazie a tutti.
Buonasera a tutti.
Grazie.
Va bene. Allora, buonasera a tutti quanti. Ok, bye bye. Ciao a tutti.
Bye.
Ciao.